let's work through a simple concrete example to see how arithmetic coding works. So this will be example number 1. Let's take our source alphabet, which we denote by capital script X, to just be a nice small set. Let's make it 0, 1, and 2. In general, X could be some finite set like characters, but let's just make them these numerals for now. And let's consider the following probability mass function on this source alphabet. So it's going to be, we're going to have a P0, P1, and P2, and let's say that the probability of 0 is 0.2, the probability of 1 is 0.4, and the probability of 2 is 0.4. And now we need some sequence to encode. So let's say, we have some sequence here of symbols from our source alphabet x1 up to xk, and let's make it nice and short. Let's make it only of length 3. Let's say that it's, say, 2, 1, 0, some sequence from this. So it could be anything, 1, 1, 2, 0, etc. So in arithmetic coding, you can conceptually break up the encoding process into 2 parts. The first part is one in which we take this input sequence and we associate to it a subinterval of the interval from 0 to 1. And here's how you do it. So we're going to need lots of space here. Okay, so let's draw the interval from 0 to 1 here. Let's draw it. This is going to be a real test of my drawing skills to make everything work out here. So this is our interval from 0 to 1. Let's expand it out a little bit. And we're going to subdivide this interval according to the probability mass function p. So we're going to subdivide it into a 0.2 part, and a 0.4 part, and another 0.4 part. That's a little higher. So this is 0.2, this is 0.6, and the height of this this 0 chunk, let's label these chunks according to their symbols. So this is 0, this is 1, and this is 2. And the height of the 0 chunk is, of course, P0. That's how we chose it. The height of the 1 chunk is P1, and the height of the 2 chunk is P2. Now the first symbol in our sequence to be encoded is a 2. So we're going to focus down on this 2 chunk. So let's extend this out a little bit here, and we're going to subdivide the 2 chunk in just the same way as we subdivided the original interval. So we're going to have a 0.2 part, a 0.4 part, and another 0.4 part. So we could label this 2, 0, and this 2, 1, and this 2, 2. And the height of this 2, 0 chunk, let me straighten that line out a little bit. The height of this is going to be the height of the 2 chunk times P0, right? So it's P2, P0. That's the height of this guy right here. The height of the 2, 1 is P2, P1, and 2, 2 is P2, P2. Now the second symbol in our sequence to be encoded is a 1. So we're going to do the same exact thing. We're going to once again, we're going to subdivide, but now we're going to do it with the 2, 1 chunk. So let's expand this guy out over here. Try to draw this straight. 2, 1. So we're going to have a 0.2 part, and a 0.4 part, and another 0.4 part. Let me make that a little bit better. 0.2. 0.4 and 0.4. So this we could label 2, 1, 0, 2, 1, 0, 2, 1, 1, and 2, 1, 2. So the height of these last chunks are going to be P2, P1, P0, P2, P1, P1, and P2, P1, P2. Very good. Now the last symbol in our sequence to encode is a 0. So we're going to choose this chunk right here, the 2, 1, 0 chunk. And we're going to associate this input sequence with the corresponding interval. So this chunk right here corresponds, let's extend this back over to our original interval from a to b. So this corresponds to this interval right here. So this is a, and this is b. The lower edge is a, and the upper edge is b. So the interval that we're going to associate this is going to be half open. We're going to include a, but not b. That's what these square brackets mean. That means include a, and open bracket means don't include b. So what are a and b? Let's compute them. Let's do everything explicitly. So a is what? Well, it's here, so it's going to be, let's see, 0.6 plus the height of this 2, 0 chunk, and that's just p2, p0. So this is 0.6 plus p2, p0. What's p2, p0? Let's see, it's 0.4 times 0.2, which is 0.08. So this is 0.08. So we have 0.6 plus 0.08 is 0.68. And what is b? b is a plus a little bit of stuff. So it's a plus what? A plus the height of this 210 chunk right here. And the height of the 210 chunk is p2, p1, p0. We already knew that. So p2, p1, p0 plus a. p2, p1, p0 is p2, p0 times p1. So we already know p2, p0 is 0.08. So we have to multiply 0.08 times 0.4. Let's see. 4 times 8 is 32. Move the decimal place 3 places. This is 0.032. So we get that b is, let's see, 0.68 plus 0.032 is 0.712. 712. All right, so we got our interval. We have computed the first conceptual part of the process is that we got our interval from a to b, and it is 0.68 up to 0.712. So let's put a nice box around that. All right. Now, for the second part of the encoding process, we're going to do something very similar, but instead of subdividing according to p, we're gonna do binary splits. We're gonna split things in half, and we're gonna keep doing that until we get a chunk that lies completely within this interval from a to b. So we're gonna draw the picture for that in a second, but a bit of notation that will be useful is binary expansions. So what is a binary expansion? Well, everyone knows decimals. Decimal expansion of a real number between 0 and 1 would be, for example, 0.1 is 1/10, 0.01 is 1/100th, or 1 over 10 squared, 0.001 is 1,000th, or 1 over 10 cubed, and so forth. Everyone knows decimals, and we could put 10 to the 1 here. Now, what is a binary expansion? Well, a binary expansion is very similar to a decimal expansion, except that instead of using 10, we're going to use 2. Binary expansion. So decimal is like a base 10 expansion. A binary expansion is a base 2 expansion. So basically, we're just going to replace 10 by 2. So 0.1, I'll put subscript 2 to emphasize that it's a binary expansion to distinguish it from a decimal expansion. It says 1/2. 0.01 in binary is 1/4, or 1 over 2 squared. 0.001 is 1/8, or 1 over 2 cubed, and so forth. So we could put 1 over 2 to the 1 here. So, for example, if we had a number like 0.1101 in binary, that means 1 over 2 to the 1 plus 1 over 2 to the 2 plus 0 over 2 to the 3 plus 1 over 2 to the 4. And that gives you some real number between 0 and 1. And more generally, if we had some sequence, so if we had point beta 1 up to beta m, say, in binary, that means beta 1 over 2 to the 1 plus beta 2 over 2 to the 2 up to beta m over 2 to the m. So that's a binary expansion, and that's going to be handy for computing, for finding the correct subinterval for the binary sequence corresponding to a subinterval that's contained in this interval from a to b. So let's do a very similar picture over here, but now things are going to be in binary. I'll try to make this drawing nice. Oh yeah, that's pretty good. Okay. So first we're going to split this interval. Again, this is an interval from 0 to 1, just like before. And now we're going to split it in half. So let me try to get I'll try to do this as closely as possible to correct. And so that's a half, or supposed to be a half. And let's label these like before. This is 0 and this is 1. And now we're going to keep subdividing until we get a chunk that's in the a to b interval. So we're going to have to subdivide this upper chunk here, the 1 chunk. So let's do that. So if we divide this guy, we get 1, 0, 1, 1. And now it looks like this is going to be in the 1, 0 chunk. So we're going to subdivide the 1, 0 chunk. And we get 1, 0, 0, 1, 0, 1. So this is looking very similar to what we did before, but now we're just doing binary splits. We're splitting in half at each step. So now let's compute some of these numbers just to see where we stand and make sure our drawing is roughly close enough to scale. So 0.1 or 0.10 or 0.110 in binary, this is 0.1 in binary is 1/2. So this is 0.5 in decimal. What is 0.11? 0.11 in binary is, it's a half plus a quarter. So this is 0.75. 0.101 is what? 0.101 is a half plus 1/8. An eighth is 0.125, so that's 0.625. So we're trying to get down to within 0.68 to 0.712. So it looks like we're going to be in the 101 chunk. So things are looking good for being to scale here. Correspondence between these two sides. So we're going to be subdividing 101. And now let's see. So this we're going to have 1010. 1011. And this 1011, what is that number? Let's scoot on over and compute this guy right here. 1011 in binary is what? It's 0.625. It's 101 plus 1/16. A 16th is 0.0625. So this guy is going to be 0.625 plus 0.0625. What's that? That's 0.6875. So where do we stand? Oh, okay. So we've got a number now in the interval from a to b. 0.1011 is in the interval, but we're not done yet. We have to keep going until we get a chunk that lies within this interval completely. And the upper part of this chunk is still 0.75, which is outside, so we got to keep going. So we keep going. We get 10110, 10111. What is 10111? 10111 in binary? Well, we have to add something to this. We have to add, what is it, a 32nd, 1 over 32 to this. And let's see, this was 1/16. 1/32 is half of that is 0.03125. So if we add 0.03125 to this, 0.6875, what do we get? We get 0.71. What is it? 71875. Yes. Okay, so now where do we stand? Are we in, is this chunk 10110? Is that contained in the interval? Nope, not quite, because we're still above 0.712, so we have to do, let's see, we have to keep going yet again. So we divide one again here. We get 101100 And now let's see, is this, what is this number here? This is 0.101101 in binary is what? It's this plus 1/64th. 1/64th. Let's see. I'm not going to do this one by hand. I've done this. I did this ahead of time. So, well, it's not too hard to do it by hand. Let's see. So 1/64 is half of this. 0.0156125. Oh, maybe it's getting ugly. Oh, sorry, that wasn't right. That's 0.1625 to get the 5. So let's see. Well, maybe we can do it. So 0.6875 plus this guy is what? It's 0.697. Let's see. 7. Let's see. This plus 0.015625. 0.7023 125. Is that right? Yes, that's right. Okay, so I checked that. I worked that out ahead of time, and that's right. Okay, so 0.703, blah, blah, blah. So what do we get? Where are we? Where do we stand? And yes, okay, so 0.703 is inside our interval, so that means that this last little chunk right here, this tiny little sliver, 101100, is indeed in our interval. So at long last, let's, this is the winner right here. This tiny little guy is our winner. So we can extend that back over to here. So this is all the way through to here. You get the point. This is our interval that we're going to use. And so we're going to encode. So this is here, just to be clear. So this is 0.1, or maybe I'll just write. So it's 0.6875. This one up to 0.703 and some stuff. And so we're going to encode this original sequence using the binary sequence 101101. Rather 101100. Encode 210 as 101100. This is the encoded sequence. So that's it. That's how you encode with arithmetic coding. So let's put our result in a nice box here. So just to summarize, I think conceptually, when you see the picture, it's not that hard. It takes a little while to sort of go through it, but conceptually, it's pretty straightforward. So we had our PMF here. We did this subdivision process first to find the interval from A to B corresponding to our sequence 210. And then we did something similar, but with binary splits. And we kept going until we got a chunk that was contained completely within the corresponding chunk here, 210. And then we encoded the original sequence using the binary sequence that was that for that chunk, for the chunk that was in that 210 chunk. Now, how are we going to decode this thing? You may be a little bit concerned at this point about being able to uniquely recover the sequence 210 given this sequence. And so let's see how that happens. There's this, as I've given it to you, the encoding isn't quite complete. So how are we going to modify this to make sure we can decode? Well, one way is to encode the length of the original sequence along with this 101100 sequence. So if we knew that the original length was 3, this is a sequence of length 3, then how would you decode this? Well, you know you have your encoded thing here. So this is maybe I'll put here 101100. You could compute the number here and the upper number, and you could start over here and do the same exact process, right? You have your PMF, that's given, that's assumed that you know that, and you're given this 101100. And so what you do is just the same thing as during the encoding process. You subdivide, 0, 1, and 2, and you see that this interval here, this purple interval, is within the 2 chunk. It's in the 2 chunk. So you would say, okay, the first thing must have been a 2. So you say this must have been 2 right here. Circle that. The first symbol must have been a 2. And now, maybe I'll draw okay, so you can see it. So now we subdivide the 2 chunk, and you say, oh, okay, the purple interval, the interval that was encoded, is within the 2-1 chunk, right? It's inside here. This is. So you say, oh, the next symbol must have been a 1. Okay. And I know that the original sequence was of length 3, so I've got one more to go. And when I subdivide the 2-1 chunk, I see that, that the purple interval is contained in 210, and so therefore I know that the third and last symbol must have been a 0. So that's one way to approach, to make sure that you can decode. Let me put it down here. So we have decodability. So this is a remark on how to ensure that this is decodable. So the first approach is to encode the length of original message. In this case, 3. So that's one option, but and I think you can probably see why from just that little argument I made as to why this does ensure that you can decode. But another and better way, for more general types of sources, for the simple source that I described above, which is in fact sort of an IID type of source, they're basically the same. But for more general, more complex sources, a better approach is to use an end of file symbol. So option 2 is use end of file symbol. What do I mean by an end of file symbol? So an end of file symbol is going to be one of the symbols from our source alphabet. We're going to designate one of these symbols to always occur at the end of the sequence to be encoded, and only to occur at the end of the sequence. So I'm going to typically use 0 for our end of file sequence, and I conveniently chose this particular sequence so that 0 only occurred at the end, and it did occur at the end. So 210 is valid with respect to that end of file symbol convention with 0 as our end of file symbol. So for example, other sequences that would be valid would be like 21120 or 1210 and so forth. But sequence so these are valid for end of file. Invalid, of course, some invalid sequences would be something which didn't have 0 at the end, like 21121, or something which had a 0 somewhere else, like 20121. Even if it ends in a 0, that's not valid. Okay, so how is this going to help us? How is this going to ensure that we can decode this original message? Well, it's very similar to when we knew the length. So what's going to happen over here? So let's say, so now we don't know what A and B are, remember? We just know this interval right here. We know 101100. So we know that we know that we're trying to, that we encoded something, that this interval, this purple interval, was contained in the final A and B. So if we start out, we start out the same. We subdivide the interval from 0 to 1 into these three chunks, and we say, oh, the purple interval is contained in the 2 chunk, and so 2 is not the end of file symbol, so there must be more to go. So we know the first symbol was a 2, and now we subdivide the 2 chunk. We have a 2, 0 part, a 2, 1 part, and a 2, 2 part. The purple interval is contained in the 2, 1 chunk. So we know the second symbol was a 1, and that's not the end of file symbol, so we keep going. We keep going, and we say subdivide 2, 1. We get these 3 chunks, and so we see the purple interval is contained in 2, 1, 0, so we say, oh, the third symbol was a 0, and 0 is the end of file symbol. 0 is the end of file symbol by our convention that I'm choosing. And so we know that we are at the end of the message, and so we spit out 2, 1, 0, that must have been the original message that was encoded. So that's decoding, how to decode with arithmetic coding. Now, one final point I'd like to make in this example is you may be concerned that, you know, okay, this worked fine for this nice short sequence, but what if we have a really long sequence? You know, this interval here, this A to B, it's going to be extremely small. You know, if you were to keep subdividing this, it already is getting tiny, but it would be just super, super small, the difference between B and A. And so if you were actually trying to implement this on a computer, you would be in serious trouble because you're going to run out of precision. You know, you can only represent a finite amount of precision. And eventually, you know, you're going to lose all precision, and this is just going to break down completely. So what I've described here is the infinite precision version of the algorithm. But it turns out that, in fact, you can modify this to use only finite precision and still get very, very good results. Very essentially, you know, empirically, the results in terms of the amount of compression that you get are very close to the theoretical compression of what you would get with the infinite version. And the way you do it is by periodically rescaling the intervals. After you subdivide and then you rescale things, you blow things back up again. But you have to do it in a very careful way, and there are some subtleties to make sure that you round off in a consistent way. And it's quite subtle, but we're going to talk about that later. And before we get to that, though, it's easier to get your head wrapped around the infinite precision version. So we're going to stick with the infinite precision version for a while, and then later we'll talk about how to modify it to actually get a finite precision version that you can actually run on a computer. So let me write that down. So down here, precision. So this can implement using finite precision. By rescaling. And exactly what I mean by that, there's some clever things that you have to do to make sure that you round off in a very consistent way. All right, so that was our first look at an example of how to implement, what arithmetic coding basically looks like.